49 years after launch, Voyager 2 is still talking to us. That alone is the real story, and once you understand everything this one spacecraft has quietly accomplished along the way, it starts to feel genuinely unimaginable that it's still out there at all. Built in the 1970s, running on power that fades a little more every single year, Voyager 2 is currently drifting through interstellar space, over 12 billion miles from home, carrying instruments that predate the modern computer entirely. And it's still sending back real, scientifically valuable data from a region of the galaxy no other functioning spacecraft has ever directly measured. What makes this remarkable isn't one single dramatic new finding. It's the accumulation of everything this one spacecraft has quietly kept doing, decades past its expiration date, at almost every stage of its impossibly long journey. To understand why this matters, you have to understand just how limited Voyager 2's original mission actually was. Launched in August 1977, the spacecraft was designed for a mission expected to last only a handful of years, focused on flying past Jupiter and Saturn, gathering close-up data and photographs that, at the time, represented humanity's best opportunity to study the outer planets directly. Nobody involved in planning that mission seriously expected either Voyager spacecraft to still be operating, let alone still breaking new scientific ground nearly half a century later. The technology on board reflects exactly how much time has passed since that original launch. Voyager 2's onboard computer systems have a combined memory measured in kilobytes, an amount so small that a single modern smartphone photograph would overwhelm its entire storage capacity many times over. Commands sent to the spacecraft still rely on programming languages and command structures designed in the 1970s, meaning the small team of engineers still operating Voyager 2 today must work with documentation, and, in some cases, institutional knowledge passed down carefully from earlier generations of mission staff, simply to safely interact with systems this old. Instead, Voyager 2 kept going. After completing its original mission at Jupiter and Saturn, it continued outward, taking advantage of a rare planetary alignment that occurs only once every 176 years, allowing it to become the only spacecraft in history to fly past Uranus in January 1986 and Neptune in August 1989. No other mission before or since has ever reached either of these two distant, strange worlds, and none is realistically expected to arrive at either one again until sometime in the 2040s at the very earliest. What Voyager 2 found at both planets genuinely reshaped planetary science. At Uranus, its instruments discovered a magnetic field tilted a staggering 59 degrees away from the planet's rotational axis, and offset dramatically from the planet's physical center. Breaking a model of planetary magnetism scientists had confidently relied on since studying Earth, Jupiter, and Saturn. When Voyager 2 reached Neptune 3.5 years later, it found the same basic pattern, a magnetic field tilted 47 degrees, and significantly off-center, confirming this wasn't some strange, isolated anomaly unique to Uranus, but a genuine shared characteristic of ice giant planets more broadly, a category of world now known to be among the most common types of planet found throughout the galaxy. This finding didn't just add an interesting footnote to planetary science. It forced researchers to develop an entirely new explanation for how these magnetic fields might actually be generated, proposing that Uranus and Neptune, unlike Earth, Jupiter, and Saturn, might not rely on a deep, stable, well-organized dynamo at their core at all, but instead generate their tilted, chaotic magnetic fields within a thinner, more irregular shell of electrically conductive material closer to their outer layers. The theory remains an active area of research even today, refined through computer simulations rather than any direct follow-up measurement, since no spacecraft has returned to either planet since Voyager 2's brief passes decades ago. At Neptune, Voyager 2's cameras also captured a massive storm system roughly the size of Earth, nicknamed the Great Dark Spot, alongside wind speeds exceeding 300 miles per hour, the fastest sustained winds ever recorded on any planet in the solar system. Despite Neptune receiving barely more than 1,000th of the sunlight that reaches Earth. And at Neptune's largest moon, Triton, Voyager 2 discovered active geysers erupting from the surface, making it only the third body in the solar system. Alongside Earth and Jupiter's moon, Io, confirmed to have active geological activity observed directly on a moon so cold that scientists had confidently expected it to be a geologically dead world. All of that happened before Voyager 2 had even reached the edge of the solar system. In November 2018, Voyager 2 crossed the heliopause, the true boundary where the sun's influence finally gives way to interstellar space, becoming only the second human-made object in history to leave the solar system entirely, following its twin, Voyager 1, by about 6 years. But Voyager 2's crossing offered something Voyager 1's couldn't. A still-functioning plasma science instrument, an instrument Voyager 1 had lost back in 1980, allowing scientists to directly, immediately measure the density and behavior of interstellar plasma for the very first time in history, rather than waiting over a year for an indirect confirmation the way they'd had to with Voyager 1. This distinction mattered enormously to researchers. When Voyager 1 crossed the same basic boundary in 2012, scientists had to rely on a lucky burst of solar activity, sending a shockwave outward that took over a year to reach the spacecraft, causing the surrounding plasma to vibrate in a way that allowed researchers to calculate its density only indirectly. Voyager 2's still-working instrument meant that for the first time in the history of space exploration, scientists could watch this crossing happen in real time, gathering direct measurements exactly as the spacecraft moved from the solar wind's influence into true interstellar space. What that instrument found genuinely surprised researchers. The plasma just beyond the heliopause was measurably warmer than existing models predicted, forcing scientists to reconsider basic assumptions about how much residual heat and ongoing physical activity actually exists in the interstellar medium immediately surrounding our solar system. Particles appeared to leak through the boundary in both directions, suggesting the edge of the solar system isn't a clean, sealed wall at all, but something closer to a porous, actively mixing zone, allowing material to cross continuously rather than being cleanly separated on either side. And the magnetic field on the interstellar side of the boundary showed a strange, unexpected alignment with the field still present just inside the heliosphere, a puzzle first noticed at Voyager 1's crossing that Voyager 2 helped confirm wasn't simply a fluke unique to a single location, since the two spacecraft crossed the boundary at entirely different points along the heliosphere's outer edge. Then, in July 2023, Voyager 2 nearly went silent for good, not because of any dramatic failure, but because of a single, small error in a routine command, one that accidentally tilted the spacecraft's antenna just 2 degrees away from Earth. Across a distance of over 12 billion miles, that tiny misalignment was enough to sever contact entirely. For roughly 2 weeks, one of humanity's only 2 functioning windows into interstellar space went completely silent, and engineers genuinely didn't know whether they would ever hear from it again. Recovering the connection required an extraordinary, rarely used technique some engineers involved in the effort informally nicknamed the Interstellar Shout, an unusually powerful command transmitted from the Deep Space Network's most powerful antenna, essentially attempting to shout loud enough that even a spacecraft no longer precisely aimed at Earth might still catch enough of the signal to respond. On August 4, 2023, that gamble paid off. Voyager 2 successfully reoriented its antenna, and full communication was restored. That close call revealed something important about the nature of this entire mission. The connection between Earth and Voyager 2, maintained continuously since 1977, was never some permanent, guaranteed link. It's an extraordinarily thin, precise thread, dependent on a tiny antenna remaining oriented with remarkable accuracy across an almost incomprehensible distance, a connection that a single, small human error can sever almost instantly, with no immediate certainty it can ever be restored. And still, Voyager 2 kept going. Today, engineers continue the increasingly difficult work of keeping this aging spacecraft functioning at all. Its power source, a radioisotope thermoelectric generator relying on the steady decay of plutonium, loses a small amount of output every single year, a decline that cannot be reversed or refueled. Mission engineers have had to shut down instrument after instrument, and even backup heating systems, simply to preserve enough power to keep the spacecraft's most scientifically valuable systems running for as long as realistically possible. Each of these decisions represents a genuine trade-off, a specific measurement or capability permanently sacrificed in exchange for a few more years, or in some cases just months of continued operation elsewhere. This is, in many ways, the most remarkable part of the entire story. Voyager 2 isn't simply an old spacecraft that happens to still be working. It's a spacecraft that has been kept alive through decades of careful, continuous human effort, engineers making increasingly difficult choices, one instrument, one heater, one command sequence at a time, to stretch a mission that was only ever designed to last a few years into one now approaching its 50th. There will come a day, likely within the next several years, when Voyager 2 finally falls silent for good, whether through a final unrecoverable power failure or perhaps another small error, this time without a successful recovery. When that happens, humanity will lose its only 2 direct sources of real-time data from beyond the edge of the solar system, at least until some future mission, one not yet built, eventually follows the same path outward, a journey that, based on current mission planning, likely wouldn't begin for decades. Until then, Voyager 2 remains out there, carrying its golden record of sounds and images meant to represent life on Earth, still transmitting real data back across a gap that now takes over 18 hours to cross, one way, at the speed of light. Every single day it continues functioning represents genuine, borrowed time, technology built in the 1970s, using computing power far less capable than a modern digital watch, somehow still gathering data from a region of space nobody had ever directly measured before it arrived there. That's the part worth sitting with. Not a single dramatic new discovery arriving on cue at the 49-year mark, but the sheer accumulated improbability of everything this one spacecraft has already managed to accomplish at Jupiter, at Saturn, at Uranus, at Neptune, at the true edge of the solar system, and now, quietly still, from somewhere out among the stars. 49 years, and it still hasn't stopped. What else might it manage to tell us before the silence finally comes?